Okay, so for the next Tracker Lab, this one's going to be a little bit different compared to what we've done in the past. And for this one, I want to start off by walking you through kind of the idea behind what we're going to be doing, so you've got an idea of what it is we're looking for each time, because we're, as I said, going to do something new. Now, we're going to be looking at circular motion. Circular motion can be kind of hard to work with unless you have a really good video. So, we've got me here, presumably, spinning around an object of some mass on a string, and I've got it connected just like we saw in class, where I've got it connected running through a tube and connected to a spring scale. So I swing it around and the spring scale goes up and down, but I try and keep it centered around a given value, and those will be marked on the videos that you work with. Alright, the first thing I want to talk about is the actual position. And so we've got the center of the circle here at the origin, you could say, and the object is out here on the outside edge of the circle. Now, we could keep track of both x and y positions, so my x could be this, my y could be this, and my r, my radius, is from the very center out to where the object is. Now, one of the things that I want to point out, if you look at this as, say, the unit circle, for instance, we can get our y-coordinate by having it equal to r sine theta, and our x-coordinate as r cosine theta. And as we're swinging this around, I may fluctuate a little bit in the radius, but I should have it pretty constant. Now, you've worked with the equipment as well. You can tell that it can be hard to keep this under the best conditions. So we're not necessarily expecting the best outcome from this, but we're going to give it a try. So, I did want to bring up that the y position will be seen as r sine theta, and the x position would be r cosine theta, and we would be swinging this through at kind of a constantly changing theta. And so that's one thing that we'll talk about a bit more when we get to rotational mechanics, but for now, I change the angle theta at kind of a constant rate. So the main reason that I bring this up is, when we start doing the track on these, you're going to notice that the position versus time functions start looking like sines and cosines. Well, that's not an accident. That's actually because our x position is r cosine theta, and our y position is r sine theta. Even if we're somewhere else, so if I'm rotating over here on this side, we still have about the same radius. We have a new angle theta here, measured with respect to the positive x-axis. But you see that we still end up with x equals r cosine theta, although that one will be a negative value, and y equals r sine theta back over here. Now, you can go through and you can double check these, but I just wanted to point those out. And we're also going to be seeing at any given point, when we look at the position versus time graphs, we're going to be seeing sines and what appear to be sines and cosines. I should be more careful with what I say. All right, the other thing that I'll say is this: because these are vectors, we could take our x position squared plus our y position squared, and that will give us our radius squared. So, at all points during the rotation, we should have it where the radius, whatever that is going to be equal to the square root of our x position squared plus the y position squared. Now, normally I'd have you go through and actually calculate this up in Excel, but one of the things that I'm going to have you do is, it turns out that Tracker is actually programmed to do this already. So I'm going to show you to look for that one. Although you could go and double check it by pulling the x's and the y's and putting them into Excel and actually calculating up the r. Alright, next. As this thing spins around, it will have what's called a tangential velocity. Now, we talked about that a bit in class, depending on what point you're watching this video at, where objects try and move in straight lines unless a force is applied to them. We have a centripetal force being applied by the force of tension, the string, that is now pulling this in a circle. Now, we're going to take a closer look at that here in a minute. It turns out that it's actually the combination of the tension and gravity, depending on which point you're looking at. Regardless, as this thing is moving in a circle, at all points, its instantaneous velocity is going to be tangential to the circle. In other words, it's trying to move in a straight line, and we're constantly pulling it into the circle by applying a centripetal force. So, I can also look at this tangential speed, the total speed, or the total velocity, if you'd prefer, As I should be more specific, it is technically the total velocity because it does have direction. And it has components. We have the y component and we have the x component. And they'll function just like a regular vector. Now the reason I keep saying speed is what we're going to find is just the magnitude of the velocity, because as this thing rotates around, it will constantly be changing. We can see back over here, it's pointed tangentially to the circle once again and pointed in a very different direction. Now ideally, in uniform circular motion, the speed would be constant. I did my best to try and keep the speed constant, but there's only so much that I can do, so the speed will probably fluctuate some throughout this. What we're going to do is we're actually going to be looking for some of the averages, but just the same, we can find the value of, or I should say the magnitude of our velocity vector by taking its x component squared plus its y component squared, and then taking the square root. So just like the radius, we can also find the magnitude of the velocity by taking the individual components, squaring them, and adding them together. All right, finally, let's talk about the forces. Newton's second law says that the sum of forces equals the mass times the acceleration. Now, in this case, I've colored it purple because we're constantly changing our direction with this circular motion thing. And for circular motion, our acceleration has to be a very specific acceleration, the centripetal acceleration, v squared, the speed, divided by r, or v squared, the magnitude of the velocity vector. So we're ignoring the direction because the direction is constantly changing, but it's v squared over r. Now, sum of forces needs to be equal to our mass times the centripetal acceleration, which means it'll be equal to our mass times v squared over r, and that's the main way that we look at it in class, where we have mv squared over r is actually what we refer to as the centripetal force. I prefer the centripetal force way of looking at it, but both are perfectly applicable. Now our centripetal acceleration, v squared over r, is what the mass is actually multiplying by, and our sum of forces must come up to that if we have something moving in a circle. Or said another way, all of our forces must add up to be the centripetal force. All of the forces must work together to be a centripetal force to actually pull this thing or push this thing or anything else into a circle. If you've got something moving in a circle, all of the forces add together to be a centripetal force that has the form of mv squared over r. All right, now that we've got that, at all points, just as a reminder, r is going to be equal to the square root of x squared plus y squared, our actual position. Our speed, the magnitude of that, or of the velocity vector, so our speed will be equal to the square root of our speed in the x direction squared, or our velocity, I should say, plus our velocity in the y direction squared, and then take the square root. And at all points, our sum of forces must come up to the centripetal force. So let's look at some of the forces in uniform circular motion in vertical motion. So when it's at the very top, the force of tension and the force of gravity work together to help point towards the center to be the centripetal force. Now I put a negative Fc here because our centripetal force points downward, and we need to keep track of that. This is where the force of tension will be a minimum because gravity is helping pull this thing in a circle. Over here, when it's on the side, gravity is pulling it down, but the main thing that we're actually looking at is at this individual moment, the force of tension is serving as our centripetal force, pulling it towards the center. Now, the force of gravity at just this moment, when it's aligned like this, is just going to slow this thing down a little bit, and that's again why my speed is going to change a little bit with this being vertical motion. In short, at this moment, we should find that our force of tension should be pretty much equal to our centripetal force. And since it's a minimum at the top, and as we're about to find out, a maximum at the bottom, this should be a pretty good intermediate value. It may not be the exact average, but it should be kind of in the middle of the minimum and the maximum. All right. Finally, at the bottom, the force of tension must beat out the force of gravity and also pull up enough to supply the centripetal force. Gravity is not helping us move this in a circle, so we have to counter gravity and also supply all of the centripetal force. So it's our force of tension that's actually pulling it up into a circle. But like I mentioned before, all the forces must add together to be the centripetal force. All right, this is where our force of tension is going to be a maximum. Now the one that we're actually interested in is when it's on the side. Our radius r should be roughly constant. It'll fluctuate a little bit because my hand moves some and I may adjust the radius ever so slightly while I'm trying to keep the apparatus going at the same rate. We can take the average for a good value on r. Our speed will likely fluctuate as the object goes up and down. If we take the average, it should be pretty close to the speed on the sides of the motion, which is where we're looking at, because this last part, the scale I read as I swung the object up and down, the scale I read as I swung the object, it went up and down, but should be centered around the listed value in the videos that we're about to take a look at. And that will be very close to the tension, Ft, when the object is on the side as shown. In other words, that should be where our force of tension is pretty close to our centripetal force, what we're actually trying to measure. All right, so finally, the last thing that we're going to do, I'm going to give you a heads up of what we're going to graph. Our force of tension should therefore be pretty much equal to our centripetal force, and therefore it will be mv squared over r. Now, what I could do is I could graph the force of tension versus v squared over r, and my slope will be the mass of the object. So that's one thing that you could do. Now the problem is, what we're going to be looking at with that might be, well, I guess actually what I'm going to have you do does change the force. So you can do that if you'd like. What I'm going to walk you through instead, however, is multiplying both sides by r, and we're going to take, moving the r over to the other side, we're going to take the radius times the force of tension versus our speed squared. That will also give us a straight line, or at least it should. We're going to find that it might fluctuate, because this one's one of our least precise labs that we've done with Tracker thus far. But ideally, it should give us something very close to a straight line with a decent value of the slope being the mass. I'll go ahead and tell you this. I measured the mass of the object that you see in the videos, and it comes up to about 94 or 95 grams. So we're going to see how close we can get to that. All right, here in just a moment, I'm going to take you through what you need to do with Tracker. Okay, so here we are. We're going to go through the part with Tracker. Now, this one's going to be a bit different than what we've done before, because usually we're copying data out and putting it into Excel and doing a whole bunch of stuff. This one's going to be a little more time consuming, but it's going to be easier on some of the analysis. So import video came up in the Tracker folder again, so I'm going to go to Desktop, Tracker Labs, and this time TrackerLab005b. Don't know why this mouse is giving me a little bit of trouble, but that's okay. So let me give you a heads up. We've got 6 different videos that we're actually going to be taking a look at. But don't freak out. It may take a little bit of time, but the data that you're looking for will actually be pretty easy to get. All right, to give you an idea, they're each for TrackerLab 5, and they say force followed by a number. Now, the first two are 3_5. That actually means a force of about 3.5 newtons was the average on the scale when I was actually swinging the thing around. The next one is 5_5. That's 5.5 newtons. It turns out computers don't like it when you put periods in the name of stuff, because it ends period like MP4. The rest of them are pretty easy to read. We've got 6 newtons, 7 newtons, 8 newtons, and 9 newtons. So here's what I'm going to do. I'm going to go over to Tracker, or I'm sorry, not Tracker, Excel. I'm going to click a little away from the edge just because I like doing that. My normal force, or not normal force, sorry, our force that we're going to measure in newtons, we have one that's 3.5, one that's 5.5, 6, 7, 8, and 9. We're going to try and take a measurement of the radius, r, for each of them, and we're also going to try and find our average speed, v, and that's in meters per second. All right, so I've got those set up, and we are going to make a graph like we normally do, but here's what we're going to do. This time, we're actually going to collect the data ourselves. All right, I'm going to bring in the 3.5 Newton one, and it may take a moment to actually go through and do this. But I'm going to show you how to do this on 1 or 2 of them and then kind of go through quickly on it. And then I'm going to try and make a supplemental video where I show you a more thorough way that we could do this. I thought about having you do that, but it's a lot of extra work, and this, what I'm about to have you do, seemed like a good middle ground. Okay, so here I am, and I'm swinging around the little whirligig, so we can see it go there. Now, I did pretty well in making certain that nothing in the background matched it, but when you go long enough, sometimes the computer will find a weird match, so hopefully everything will be fine on this. We're not going to bother trying to cut this down. I got some help on this one, so we're in the middle of things, right when hopefully it should be pretty close to, as I mentioned, 3.5 newtons. So we're going to go straight to calibration. We're going to teach this thing 1 meter. We've got a meter stick right next to me propped up on a chair so that we can see it. This is not 100, it is 1.0. So I'm going to put that there, and then I'm going to put the origin right over here where my hand is, where the center of the string is. Now, as I move things around, my hand will move a little bit, and that may throw off our radius value, but it's going to be okay. We're going to see what we come up with. All right, so I'm going to hide that, and on this one, we're just going to go straight to create point mass. I think there's something wrong with this mouse. It's not the one normally with the computer, so. All right, we're going to do auto track because otherwise we'll be here for the rest of our lives. So hold down Control and Shift, and we'll be able to see the circular crosshair. And I'm going to click on the red part of the little thing. I'm going to drag this down, and on this one you may want to watch it as it goes so that we know it doesn't accidentally lock on to something else. That happens from time to time. Now here's what we're going to do. Down over here it says frame 26 up through 30, 35. Let's get about 200 frames worth of data. Ideally what I'd like is to let this thing go up and down for a couple of complete cycles. Remember what I mentioned before, that our position, x versus time, should actually look like either a sine or a cosine depending on when we start it, and this one's actually pretty cosine. You can see it filling in right now. Now it's got some sharp edges, but part of that is when you look closely, Tracker's having a little bit of trouble tracking the exact same spot, but it is following the actual whirligig thing itself. So even if we're off by a little bit, we're still okay. Though that does give us an idea that it's jumping kind of from one side of the cup holder to another, and so, we're coming up on 200 frames, so I'm going to let it go just a little bit longer, but it does jump from one side of the cup holder to the other, and that's probably about 4 or 5 inches, so we've probably got a little bit of wiggle room in this one of the better part of, hang on just a moment, I'm going to try and stop this on a complete cycle when it's at the top. There we go. That should be pretty good. See, it started at the top, so I'm going to try and let it end where I have it about to repeat back over here. Now, it's not a big deal, but it's more likely to get us kind of the results we're looking for. Finishing up what I was saying, we know that this thing isn't tracking it perfectly, which means we may have a little bit of wiggle room in this. The size of these cup holders is probably about 4 inches, so that's about 10 centimeters. So that's something that we should take into account. On any measurement that we've probably only got it to within about maybe 10 centimeters. All right, so here's where we're going to do what's going to be a bit different in this one. When you come up to the graph here, you'll notice that it's T and X. Well, one of the things that we haven't looked at yet is if you hover over it, there's a box, you can click on it, and it gives you a whole bunch of options. Well, I can bring up the Y. Well, remember how I said that the Y should also look like a sine or a cosine? We do actually have that. This is our Y position. There's one other thing that, well, many other things I should say, but one other thing that we're going to look at immediately that Tracker does. R, position magnitude. And it calculates it just like we said earlier. It does x squared plus y squared and then takes the square root of it. In fact, it's the thing that we're actually looking for. Now you can see from this graph, it's kind of crazy town banana pants. It's all over the place. But I do see that the top of the graph, we get up to kind of the maximum a couple times of about 0.5. Now remember, we set our calibration over here, so that's 0.5 meters, that's half a meter. And on the low end, it's probably a little bit beneath maybe 35 centimeters. What I'm looking for is I'm kind of looking for the tops and the bottoms, and I'm going to try and find the average in the middle. So this might be something, it's a little above 0.4, but I wouldn't put it as far up as 0.5. We might have something here, maybe 0.42. And here's where I'm going to leave this to you and why this one's a little bit trickier. This isn't the best measurement that we've ever done, and this one seems to be even lower, maybe because my hand might start shifting. But I want you to try and do a little bit of guesswork on this. Now you could do 0.42. In fact, I think I'm going to call this 0.40. So I'm going to come over here, 0.40 for my radius for force equals 3.5 newtons. Great. The other thing that we needed is the velocity, the magnitude of the velocity. Well, Come over here, click that again, and you'll notice that down a little ways we have the velocity in the x direction. You'll notice that it also appears to be a sine or a cosine, and the velocity in the y direction also sines and cosines. Interesting to note. All right, but the important one is, just beneath that, it says velocity magnitude. Here is where it does vx squared plus vy squared, and then takes the square root. It's something built into Tracker. Now we've got something really high up here and here. I think that's a fluctuation. We can kind of see it going up and down here. I would say that our average, our midpoint's probably just a little bit below 4. I'm going to call it maybe 3.8 meters per second. Now, this is not one of the most precise labs that we've ever done. I freely admit that. But the alternatives for you all would be very time consuming. So this is basically what I want you to do. Now this was for 3.5 newtons. Now what I'm going to do, you can save this if you want, but now that we've got the data, it should be in pretty good shape. I'm going to do a new tab, and then we're going to move on. Import video. Let's go to the 5.5 newton. Now over here it gives you an idea of how much memory is in use. When I open up a new video, it jumped from about 25 up to 44 megabytes of 247. Now it's got a set amount of memory that it can actually work with. So if your memory gets full, you may have to close everything out and then restart the program. Now one thing that I will say is, as long as you're keeping track of your data here, you won't need to redo the other ones. In fact, I'm going to go ahead and do save as. Let's go to files, let's see, desktop. Hopefully the folder you're looking for will be exactly listed, but desktop and then Tracker Labs. I can do TrackerLab5 and then, oops, I forgot to make one, so let's make one. I'm going to make a folder called Student Data, just like the other ones that we've got. I'm going to go ahead and save mine in here, 2017, TrackerLab005b. And this one is Sanchez, so I'm going to go ahead and save that. That way, in case right now you may have heard it's raining a little bit, it'll be my luck the power goes out, and at least I can save my data. All right, moving on, I'm going to walk you through this one again just so we see it, and then I'm going to try and time-lapse the stuff for the other ones that we're going to do, because you're just doing the same thing each time. Now, as you get going, the longest thing that's going to be about this is actually having to wait for this thing to auto-track some. So I'm going to put my origin there, hide it. Let's do create point mass, Control-Shift, and I select the cup holder and click search. I'm going to watch it again. We'll do a couple complete cycles, trying to stop it on a complete cycle if we can, and hopefully we'll be in the ballpark of about 200 data points, so that way we've got quite a few that we can kind of look at and try and get the mid-range of. All right, here it goes. Now, I'm not necessarily going to make you watch the entire thing on this. After we're done with this one in particular, I'm going to go through and do one time-lapse video where it goes very quickly, basically. And then that way you can kind of see what's going on with the others and what I fill in for the data, and then we'll pick up with the final thing, which will be the graph. All right, we've got about 2 cycles here. One of the nice things is, on the later ones, the higher forces, I think it's actually spinning around a little bit faster on the whole, and so we can actually get a lot more data by the time we get to frame 200 or so. In fact, that looks pretty good. I've got about 3 hills there, so 3 complete ones. It's on its way back down, and you could imagine it would then connect over here. I've got some complete cycles here. So the big thing that we need is R. This one's, again, a little crazy, but it looks like we've got some low points down here, some high points up here. Maybe a nice mid value might be in here. Let's see, so we'll call that 0.34. And now I'm going to find my speed. Again, once you start getting going on this, it gets going pretty quickly. So it gets up to maybe almost 6, possibly, and then a little, about 4-ish, so maybe 4.8, 4.9, because it's a little below 6, so I'm going to call that 4.9. That sounds great. All right, I'm going to go ahead and stop it here, and I'll speed things up so that Okay, so hopefully that didn't take too much time. I will point something out. On one or two of the tracks, it started acting weird and it didn't track it properly. If that's the case, just come over here, hover over this. You can right-click on properties of mass A, for instance. You can click delete. I'm not going to do that. But if you have it where it tracks kind of the wrong thing or gets lost partway through the track, just tell it stop, close, delete that one, and then try doing the track again. Okay, now reading these charts isn't the easiest thing ever, so do your best on it, and remember that we've got a whole lot of error that's built into this one, so we're not expecting a whole lot of great results, but let's see what we end up with. So here's my table. Looking over the 3.5, I cleaned these up just a little bit. I went back after I had everything put together, so if I go to the 3.5 tab, I look at R. Now I've got a nice mid-range, high point, low point, low point, high point. We've got maybe 0.4, maybe a little bit above that, and so 0.4. And for our speed, 4.1, I've got probably about 4. I could call that 4 meters per second, 4.0. I went through and I double-checked a number of these, tried to get them as close as I could, but again, the graphs look a little weird and it's hard for us to make all these measurements. That's okay, let's see what we end up with. Now here's where we're going to bring back up what we had mentioned before when I walked us through with the PowerPoint. Now there are a couple things that you could do. Let me back up some. We could do the force of tension versus our speed squared over r, or we could also do what I recommended, our radius times our force of tension equals our mass times v squared, our speed squared. So I'm going to do my y-axis for mine, r times f, and I'm going to have the x-axis be v squared. You can do whichever one you'd like, but see what you come up with. So over here I'm going to do r times f, and that will be meters times newtons, will be the units. And over here I'm going to do v squared, which will have units of meters per second quantities squared. Great. So equals, let's do f times r, or r times f, that sounds great. And then over here on our speed, I'm going to do equals my speed squared raised to the 2, however you'd like to do that. All right, then I'm going to highlight both of these and then drag down the little square like we've done many times before. Great, now I've got those and we're going to make our chart and we'll be pretty much done. So our scatter plot, going to bring it up here, right click, do select data, add, and we could call the series name force times radius versus speed squared Sanchez. Huge name, but that's what happens. All right, so we want the x values. I said that was going to be our speed squared. And our y values were going to be our radius times our force. Let's see what we come up with. Now, this one's not a beautiful line. We can see that it kind of squiggles up some, squiggles down some, and we have two that are pretty much right on top of each other, which is interesting. But let's see what we get on our trend line. So I'm going to add that and display equation on chart. You know, it's not our best one ever, but it does actually look kind of linear. We can see that we've got kind of the spread as we continue back up over this way. It might be nice to take a lot more data points, but now, according to this, since I have force times my radius as my y, and my speed squared as my x, the slope of this line should be our mass. Now, I made a measurement of about 0.081, and when you check your units and all of that, that comes up to about 81 grams. Now, the actual mass of this thing is about 94 grams. Did we expect to get that close? Well, we're not that bad. Like, I didn't find that it was 1 gram, and I didn't find that it was 10,000 grams, but we are noticeably off. We're about 10% off. But remember, I mentioned before that this will probably fluctuate by about 10 centimeters, and we're looking at this stuff, which is very noisy. It's hard to get exactly what we're looking for, and we're looking at it by eye. So this isn't bad. I'm going to go ahead and run with this. Now we can do the usual things of cleaning this up a little bit. Honestly, the big thing that we want, because these numbers aren't bad at all, what we're going to do is we're going to add chart element, axis titles, primary, And if nothing else, as long as we've got the units, since we've got the proper name up there, that should be fine. So I'm going to call this meters per second quantity squared. And then we're going to add another chart element, axis title vertical. And we're going to call this one meters times newtons. There we go. All right, so here's our graph. The numbers actually look pretty decent. Everything seems kind of fine with this. So this one will be just fine. Now, here in just a moment, I'm going to take you through and I'm going to show you that instead of eyeballing this, which is what we did here, I'm going to load this back up and I'm going to show you something that's far more complicated, but hopefully will get us a better outcome on this. Now, this is all I want you to do because the far more complicated, I've already decided, is not what we're going to look at. So I want you to eyeball this. If it's not perfect, that's okay. What I do want you to see is, in particular with this one, while we don't have a great measurement, we do know that we've got a lot of wiggle room in all the measurements that we made, and we weren't that far off. We were about 10% off. That's still a noticeable amount, but if we had better setup, better equipment, and a couple of other options, we could probably narrow this down quite a bit. I'm going to go through and I'm going to show you that we can do something a lot better than just kind of looking at the graph the way that we have. But that'll be a supplemental video. So this is what we're looking for. You can submit this graph just like we have in the past.